start our session today. And for me, it's a great pleasure to introduce our today's speaker, Professor Oleg Zaboronski from University of Warwick, because I think that most of our audience, at least colleagues from our department of random processes, very well know his papers devoted to different processes of coalescence and relationship between these processes and such interesting topics as quantum physics and ensembles of random matrices. So we use your results very often and try to apply in our investigation. So I think that maybe this talk can be just beginning of some fruitful conversation on this topic of coalescent processes, point measures which arise there, and related subjects. Today, Professor Zaboronski will speak about probabilistic methods for the asymptotic analysis of Fredholm Determinants and Pfaffians. Please.
Thank you very much. I'm very pleased to speak at your seminar. I can't ignore the fact that my country is committing horrible crimes against the Ukraine. I'm deeply ashamed of that. I am also amazed by your fortitude that this seminar continued throughout these darkest days. And I want you to know that here in the UK, despite spiraling costs of energy, despite various financial difficulties, everybody remembers Ukraine and everybody is united in the desire to support your country. So there is no hesitation. And I hope that not only we will continue this collaboration, I hope that very soon we will be able to meet in person, either here or in Kiev, and resume our normal lives. Sorry about that.
Thanks a lot for such an important sentence for us. And me too have a hope that we will meet personally in the nearest time. Thank you.
So I will talk about Fredholm Determinant and Pfaffians appearing in the theory of interacting particle systems, which Andrei has alluded to, and I will discuss how to study these Fredholm Determinants and Pfaffians, at least asymptotically. And it is based on several papers written in collaboration by Will Fitzgerald, Mikhail Poplavsky, our former postdoc who is originally from Kharkov, and Roger Tribe from Warwick. So my plan is very simple. First, I will start with application examples. So what kind of results you can get using the asymptotic theory of Fredholm Pfaffians. And this will be heavily based on the theory of determinantal and Pfaffian point processes. Thankfully, Ekaterina Glinina gave a very nice lecture course on point processes, in particular determinantal and Pfaffian point processes at this seminar last year, and I enjoyed watching this series. So the background is hopefully there. I will then show that gap or emptiness formation probabilities, as they're known in the theory of quantum spin chains, for such point processes can be expressed in terms of Fredholm determinants of Pfaffians. So in other words, and that was the main motivation for studying general asymptotic theorems for Fredholm Pfaffians, which I'm going to cover in the second half of the talk. And then I will shortly describe how a probabilist might tackle the question of asymptotic analysis of Fredholm Pfaffians. So this is the plan. And this is my first example. It concerns zeros of Kac polynomials. And this is an old paper by Dembo and collaborators dating back to 2002. And what they've done, they considered a random polynomial. So here the degree is n-1. The coefficients are assumed to be independent, identically distributed random variables with zero mean, unit variance, and let's assume some regularity stronger than necessary. Let's say that all polynomial moments exist. And then it was shown in this 2002 paper that the probability that this polynomial stays positive decays algebraically with the exponent minus b. Moreover, the exponent itself was characterized. And it was characterized as follows. So you consider a stationary centered Gaussian process with autocorrelation given by inverse cosine hyperbolic. So as stated here. And you take the probability that this process stays positive over the interval from 0 to t capital. Okay. So compute the log of this probability, normalize by the length of this interval, and take the limit when t goes to infinity. And this gives you b. So there are several statements here. So namely that this exponent exists and that it is universal. Okay. So it's a very strong result. And what is interesting in this 2002 paper, the value of b was conjectured from a numerical simulation, but not computed. Now, and oh, by the way, please interrupt me at any moment and ask questions if I am not being clear.
Okay.
So it is not that, so the relation between this random, this Gaussian process y and the original random polynomial is not that distant. So it turns out that y can be thought of as a time change of a Gaussian power series. Okay, and now this looks like Kac polynomial, like the n goes to infinity limit of Kac polynomial, except for the coefficient gk's are independent n0, 1 random variables. Okay, so of course this series converges only when x takes values between -1 to 1, but you can sort of unroll it onto R and get y. So why am I interested in the objects like y or f? So this random function or a Gaussian process. It was shown in 2010 in the paper by Forrester, Matsumoto, and Shirai that zeros of f is a Pfaffian point process. So a time change of a Pfaffian point process is also a Pfaffian point process, which allows me to conclude that zeros of y also form a Pfaffian point process. So now you can apply one of the theorems which we use. And our theorems, so I will explain in a second that these emptiness probabilities for Pfaffian point processes are always given by Fredholm Pfaffian. We now know how to compute these Fredholm Pfaffians, so we analyze them and we confirm the numerical result of Ginibre and collaborators that B is equal to 3/4. So this is one, but a typical application of the theory of Kac polynomials. Of the theory of Pfaffian point processes to study random functions. Okay, so my second example concerns the distribution of annihilating-coalescing Brownian motions. And here's the model, which is more familiar, perhaps, to some of you. We look at instantly reacting one-dimensional Brownian motions started from every point of R. So I do not want to formalize it. For instance, you can start, with Poisson initial conditions and take the limit when the intensity goes to infinity. So in other words, we're looking at some entrance law. And what is the reaction? So at the collision time, we flip a coin, and with probability theta, particles annihilate, meaning that we remove both particles from the system. And with probability 1 minus theta, they coalesce, so we replace a pair of particles with a single one. So if theta is equal to 0, in other words, when annihilations are forbidden, we're dealing with a ratio flow here. Okay, so it is also known that for all positive times, the single time law of the process is Pfaffian. Okay, so let's denote it by X subscript T. And let me also look at the emptiness probability. So let me look at the probability that there are no particles between 0 and L. We know quite well that every Pfaffian point process, so I'm referring back to Ekaterina's lectures, so the correlation functions or correlations functions of finite order are given by Pfaffians or finite dimensional matrices. So the emptiness probabilities of this type typically are not expressed in terms of correlation functions of a finite order. The only exception known to me is exactly the Aratia flow, where the empty interval probabilities form a system of Markov duality functions for this process. But in general, you need to know all correlation functions to calculate this emptiness probability. So it's an interesting challenge to see whether the Pfaffian structure is useful for looking at these global objects. And the result turns out to be this. So it turns out that the probability of such a void decays exponentially with L, with the size of the gap. And there is some explicit order 0 correction, and then there are terms which go to 0 when L goes to infinity. Okay, so, and here are some notations. P here is the reciprocal of 1 plus theta. And there are some explicit formulas for kappa 1 and kappa 2. So for instance, the term, so for kappa 2, let me try to remind you. So we have a polylogarithm here. Okay, and I'm interested only in the values of the parameter as greater than 1, so I can get to values of the argument x equals to 1. So there is some coefficient, a function of p, given by this polylogarithm. normalized by the square root of t, and there is another contribution which is also proportional to inverse square root of t. So this is an example of Gaussian scaling. We have L, so everything depends on L over the square root of t. Okay, and I think so. What is so the only remark I would like to make about this answer is that it is fairly easy to understand why such an emptiness probability should decay exponentially. Well, you just take, so imagine the time at which you observe this void is of order 1, then it is quite beneficial to break this interval into chunks of length of order 1, and then say annihilate or coalesce all particles in each of these intervals independently. Okay, so the correlations between particles for the system decays Gaussianly fast. These are virtually independent events, so you take the product and you get the exponential decay. The constant, however, cannot be computed using these heuristics. So that's where the Pfaffian structures turn out to be useful. Okay, so let me carry on. So there is also an explicit answer for kappa 2, but I don't want to display it. It is a bit too complicated in this greatest generality. And this result was actually conjectured, amazingly enough, using a combination of numerical simulations and heuristics by Derrida and Zaitag, who studied these models in mid-90s. So this is my third and final example. Oh, I think yes, okay. Up to now, I've been working in the case which is either translation-invariant, so the process is stationary, or it can be made stationary by an appropriate time change. This example comes from random matrices. I am trying to look at Ginibre orthogonal ensemble. And what I mean is just n by n random matrix with independent normal 0, 1 entries. No symmetry, unlike the classical random matrices like symmetric random matrix model, no symmetry assumption is made. So this is quite an interesting model. It has a long history. And I think I should remark quickly about what is happening. So if you think of a characteristic polynomial of a real valued matrix, it has real coefficients. Therefore, the roots are either real or complex conjugated, right? And the result is that if n is much greater than 1, then we have approximately root n eigenvalues to be real, and the rest are complex. Complex eigenvalues are distributed uniformly in a circle of radius of order root n in the complex plane, actually not just of order root n, but root n. And if I were to draw the density of real eigenvalues, I would have ended up with something like this. Okay, I think I stopped annotating. Annotate, draw. Oh yeah. So the size of the spectral support is approximately root n. Okay. Now, I'm interested in studying just the real eigenvalues, and I'm interested in studying them near the edge of the spectrum. Okay. So for that, I take the process, the point process describing just the real eigenvalues, and shift it by root n. Now 0 corresponds exactly to the right edge of the spectrum. And it turns out that the corresponding point process is a Pfaffian point process. And this is the celebrated result of Forrester Nagao, Borodin, and Sinclair. And it was, so it took people about 40 years to calculate the distribution of real and complex eigenvalues for the real Ginibre, after they had realized that the eigenvalues for the unitary matrix model are a determinantal point process, and orthogonal matrix model are a Pfaffian point process. So this is a really tough matrix ensemble. Okay, so now I'm asking the question which is similar to what I asked before. So what is the probability that the interval from -L to +∞ is empty of, is void of eigenvalues in the limit when L is large? So it doesn't cost much to have no eigenvalues to the right of the spectral support. But if L is large, we start eating into this region where the density of eigenvalues is positive. So this becomes a rare event. And it turns out that this probability decays also exponentially. And one can calculate both the leading term, which is given by Riemann zeta up to a constant, and there is also an explicit formula for the order 0 term. Okay, so, and here, this is probably one of 2 occasions where I'm actually writing an explicit formula for kappa 2. It's, I don't know what to say about it, except for it comes from probability theory. So it's some double sum. So you probably know that when n goes to infinity, the inner sum converges to pi, so that makes the whole sum convergent. And another interesting remark is that we had, so if we go back to the model we had before and look at the model of pure annihilation, the polylogarithm in that case becomes exactly equal to this zeta function divided by root pi. The argument of the polylogarithm is going to be 1. And it's just an experimental observation. And I personally don't know any reasons for this coincidence, that the Pfaffian point process up to rescaling by time, the Pfaffian point process which describes the distribution of eigenvalues of the Ginibre ensemble in the limit when n goes to infinity, coincides with the Pfaffian point process describing one-dimensional distributions for annihilating Brownian motions. I don't know why it should be like that, but this is true. So in other words, this is, to a degree, this is a particular case of the result reported previously. Okay, so I decided not to delve into exit measures. Maybe it will come up during the after seminar discussions. So I just would like to explain how the theory of Fredholm Pfaffians links into the theory of interacting particle systems and how they can be helpful, how the computation of emptiness probabilities can be reduced to the question of computing certain Fredholm Pfaffians. Okay, so let me clear the drawings. Okay, so a lot of work will probably go to decipher each of the slides, but at least I hope that the steps are quite clear. So let me recall one of the results explained by Ekaterina. So we look at a point process, at a simple point process on R, and we say that it's a Pfaffian point process with kernel K, which is a function of two variables with valued in 2x2 matrices. If its intensities and point intensities are given by this formula. Okay, so if we're interested in the intensity calculated at points x1 to xn, what you need to do is to build a matrix out of the kernel, an n by n matrix. So 2n by 2n matrix, because K itself is a 2x2 matrix. Part of the definition is that the kernel should be such that the matrix KXI is Q-symmetric, so you can compute the Pfaffian, and that's and that gives you the definition of the Pfaffian point process. Okay, so now how do you go to the emptiness probability? So let me look at the indicator that some integer valued random variable is 0. Right, so it is, I write this indicator as 1 minus 1 to the power n, and I use the binomial expansion. Okay, so this is the formula we get. Let's remember it. And then there is a definition of Fredholm Pfaffians by Eric Rains, dating back to the 2000. So Pfaffian of a skew-symmetric matrix given in terms of some operator K acting, say, on L2 on U of U, where U is a subset of the real line. And J here is a symplectic matrix. So think of a block diagonal matrix with anti-diagonal entries I and minus I. Okay, so the definition of this Fredholm Pfaffian is given by this formula. So it's this infinite series. And this definition is motivated by two things. So if K is of a finite rank, this formula will become identical to a finite dimensional counterpart known from linear algebra. And if K is also has the same structure as J, so if it is anti-diagonal with, say, entries T and minus T, then this formula will give us a Fredholm determinant, a known expansion formula for the Fredholm determinant. Okay, so, and now I would like to combine 2 and 3. So let's look at this combinatorial coefficient and think of n, replace n with a random variable given by the number of particles in an interval u. So you know that n-point intensities are nothing but densities for the factorial moments. So n choose k is exactly 1 over k factorial multiplied by the factorial moment of the order n. In order to get this factorial moment, we just need the n-point density integrated over the case product of the interval U. So therefore, if you are interested in the probability that your process has no particles in the interval U, it is exactly this Fredholm Pfaffians. And exactly the same derivation goes through for Fredholm determinants. Okay, so
but such formula with the factorial moments can be produced, it seems, for arbitrary point process just using its densities. Yeah.
Yes, that's absolutely right. And what helps is that, oh, by the way, this is an inconsistent notation, I apologize. So you're definitely right. So a similar formula, it's just an exclusion-inclusion formula, can be written for any point process, except for instead of this explicit expression in terms of Pfaffians, you will have rho n, the intensity. But if you have a Pfaffian point process, you substitute this finite dimensional Pfaffian into this formula and get the definition of Fredholm Pfaffian. Thank you. That's a very good point. Okay, so we have, so now if you feel all the details between these steps, we have our statement that gap probabilities for Pfaffian point processes are expressed in terms of Fredholm Pfaffians. Okay, so now this is a slide where I hope to get your input on. So all Pfaffian point processes known to us, and I mean, this is Gaussian orthogonal ensembles, Gaussian symplectic ensembles, real Ginibre ensemble, Katz polynomials, coalescing annihilating Brownian motions, coalescing Brownian motions with fragmentation, annihilating Brownian motions with pairwise input. These are all examples of Pfaffian point processes where the kernel is not just an arbitrary skew-symmetric matrix-valued kernel, but it has this special structure. So all matrix elements are built out of derivatives of a single scalar-valued function of two variables. For problems related to coalescing annihilating Brownian motions, we know the reason for this structure. It is the so-called duality. So you can find a system of Markov dualities whose expectations are given by scalar Pfaffians. And when you differentiate them, you get this Pfaffian structure. And Ekaterina spent some time explaining this transition from dualities to the Pfaffian point process. Now, my question is, have you seen any other examples of Pfaffian point processes where this structure is not present? I would be very interested to know, is there something fundamental, or it's just a particularity of these integrable examples which we are considering? So, and we consider kernels of this type. So we call them kernels in the derived form, or duality kernels. And there are two cases. We look at the translational invariant case, and we start with some probability distribution, which on top of that is even probability distribution density function. In this case, K will be just an integral of rho up to y minus x. Okay, and it turns out that this form is again natural. So presenting K just as an antiderivative, I mean, it doesn't cost much, but it seems natural for all these problems. Okay. In the non-translational invariant case, the situation turns out to be slightly more difficult. We still have a probability density function, which we call ρ. It no longer has to be even, and in applications it's not even. But this scalar-valued kernel K is given by this complicated integral of the determinant of this two-dimensional matrix. And again, in all the cases, in all the non-translationally invariant cases we dealt with, this is the form. So in all cases I listed, you can get the scalar kernel to have this form. And to be honest, it's not that surprising. So the duality, the expectations of duality functions solve linear PDEs like a heat equation. So now you have the kernel itself is related to the two-point function. So it's a two-dimensional heat equation with Dirichlet boundary conditions. If you have translational invariance, you immediately reduce it to one-dimensional heat equation and you get the answer in terms of a single integral. If you have a two-dimensional heat equation with Dirichlet boundary condition, the only efficient way I know of solving it is Carlin-McGregor formula. And what is Carlin-McGregor? Well, it's of the determinant of transition densities. Okay, so this is my best attempt at explaining these complicated formulas. My real excuse is that all the cases we wanted to work with are in this form. And here is one of the outstanding problems in the theory of Pfaffian point processes. For determinantal point processes, you can look at a candidate kernel and use Soshnikov's theorems to decide whether it can be a kernel of a determinantal point process. For Pfaffian point processes, the corresponding statement is absent. So if you give me an example, I won't be able to say without hard work whether it defines an existing point process. And it could be that on the way to proving this theorem, if there are no other examples than the one I'm displaying, this form will be part of this classification theorem. Okay, so that was a romantic deviation. Now let me just indicate some very technical steps which people take on the way to the asymptotic analysis of Fredholm Pfaffians. So it is known in the finite dimensional universe that the square of a finite dimensional Pfaffian is a determinant, is the corresponding determinant. The same is true for Fredholm Pfaffians and determinants. And by using certain manipulations, you can show, and this was done originally by Tracy and Widom, that the square of Fredholm Pfaffian is the Fredholm determinant. So we have I plus some operator, and this operator is the sum of two terms. So one term is exactly in terms of that scalar kernel, which I defined, and then there is a finite rank operator. So now you can use at least some of the theory of Fredholm determinants, such as Zago's theory, in order to analyze its asymptotics. So for general orthogonal ensemble and general symplectic, Gaussian orthogonal ensemble and Gaussian symplectic ensemble, it was done by Tracy and Widom. And for the real Ginibre ensemble, it was done by Ryder and Sinclair. I apologize for not indicating the dates. Ryder and Sinclair's result dates back to around 2010, and Tracy and Widom around 1993. And in 1993, I was actually Tracy's undergraduate, not undergraduate student, but a graduate student on his course on random matrices. So, and what do you do with the Fredholm determinant? Let's use trace log formula to derive the probabilistic interpretation. And I will talk about the trace log formula after I've stated the general theorems. Okay, so what makes the probabilistic interpretation, which I still haven't explained, but will definitely do before the end of the talk, special, is that it works for the non-translational case. It allows you to formulate general theorems for the asymptotics of non-translationally invariant Fredholm determinants if your operators are of the so-called Hankel type, which play quite an important role in today's studies of KPZ universality class. Okay, so all right, so basically all I've said on this slide is that by taking the square of the Pfaffian, you rewrite it as a Fredholm determinant. Okay, so these are these general theorems. So the first, it's the theorem for the translationally invariant case. So I'm talking about the Pfaffian kernel, so this matrix valued kernel. And I want it to be in the derived form, which I showed. The scalar kernel is given by the italic k. It's this integral of density. And I would like to look at the case of the so-called thinned Pfaffian point processes. So we have an extra parameter over here where p can take values between 0 and 1. I will impose certain conditions on the moments of that density rho, the derivative of the scalar kernel r. And under these assumptions, the logarithm of the Fredholm Pfaffian of the operator restricted to the interval from 0 to L behaves, so it grows linearly with coefficients minus kappa 1 when L goes to infinity, and then there is an explicit order 0 correction, and the rest of the terms go to 0 as L goes to infinity. Okay, so there are different formulae for kappa 1 and kappa 2 if depending on the value of this thinning parameter p. But if you suppose that this effective density has the fourth moment, you can write down an explicit expression for kappa 1 and kappa 2. Kappa 1 is given by this series. And what you do, you take the n-fold convolution of rho and compute the value at 0, divide by 2n, and take the limit when n to infinity. Okay, so if rho is Gaussian, this convolution will behave as 1 over the square root of n. You just take the sum of n identically distributed Gaussian variables, and this sum becomes that zeta function I showed in one of the examples. And again, here is a formula for kappa 2. It is slightly complicated, but you also have this double sum, which we've already seen for the Ginibre case, where this, which corresponds actually to rho being a Gaussian density. So that's the first.
You see, it looks like a Bessel distribution. So maybe it explains why you have this kappa 2 in your first example, the Ginibre ensemble, yeah? Because yeah, it was exactly a value of Bessel integral, yeah?
That's right, yes. Yeah, thank you very much. Thank you very much. I didn't think about it. Yeah, thank you. This term appears in a slightly different guise in the proof. So that's probably why our eyes were short. Thank you. Okay, So this is the theorem in the translationally non-invariant case. So now I'm looking at the Fredholm Pfaffian of the operator restricted to the semi-infinite interval from, say, -L to infinity. This is an interesting case if you are interested in the behavior of, say, the rightmost particle for an interacting particle system, of the rightmost eigenvalue for a random matrix model. And again, the logarithm of this Pfaffian behaves asymptotically linearly with explicit expressions for the constant kappa 1, and there is a correction kappa 2, and the rest of the terms must go to 0. And I do not want to write down an explicit expression for kappa 1 and kappa 2. I will just notice that that the constant kappa 1 is actually equal to the corresponding constant in the translationally invariant case. Okay, so, and that means remember this picture of the spectrum for the Ginibre case. Imagine that we push deep into the spectrum. We're now in the almost translationally symmetric case. That's right, yes. So to a degree, this is a disappointing result that this coefficient is exactly the same. But here we are. Oh, by the way, this formula doesn't work for something like GOE, another example of Pfaffian point process, because the moment assumptions break. So, of course, instead of this linear power in L, in the case of GOE, you will get L to the power 3/2 as dictated by Tracy-Widom distribution. Okay, so that's the second theorem. And finally, this is my last slide. I would like to try to convince you that this purely analysis problem concerning the asymptotics of Fredholm Determinants and Pfaffians can be solved using probabilistic methods. And the idea goes back to Marc Kac, who actually, so one of the first continuous versions of Zago's theorem, known as Ahiezer-Katz theorem, was actually proved using probability theory. And here it goes. So first of all, so for all operators we discussed so far, the following expansion, which is well known in the finite dimensional case, applies. So the logarithm of the determinant is the trace of the logarithm. And then you expand the logarithm into an infinite power series and you get the right-hand side here. Okay. So now what is T here? So I can restrict myself for the purpose of this explanation to an integral operator on L2 with even translation invariant kernel, and I will normalize it. Okay, in most cases you can, so for as long as the kernel is integrable, you can move, and its integral is not equal to 0, you can remove the normalization into, you can shift the normalization into the value of lambda. And I will also, I think I forgot to say, I will also work with non-negative kernels, even though formally all these manipulations go through even for signed kernels. Right, so let me write down trace of t to the n explicitly. So, okay, so we have the integral over the cube 0 to t to the power n, and we just start stringing all these kernels together. So the first argument x1, x2, x2, x3, and we end up with xn minus x1, thus closing the loop. Let me differentiate the trace of the nth power with respect to the endpoint of the interval to which the operator is restricted. Right, so due to the cyclic property of the kernel, I will get n identical contributions, right, depending on where I am differentiating. And the integral will be over n minus one dimensional space, right? And now I will have to start from 0 and end at 0. So it is just an exercise to confirm this formula. Okay, so now, sorry, where's the probability theory here? Okay, but I think we see something. So these T's start looking like transition densities. And whatever is transitioning is not allowed to leave the interval from 0 to t. So, right, let me look at the discrete time random walk with continuous increments. And the density of these increments is exactly given by the kernel of the operator t. Okay, so let me introduce the first time my random walk leaves the interval from 0 to t. Then I can interpret this integral very simply. I'm not doing anything with this factor of n. Okay, but what my random walk starts at 0, then it moves for n steps inside this interval 0 to t, and finally exits. And it exits at 0. Okay, so if I rewrite this integral in the probabilistic terms, it will be the expectation with respect to the random walk measure of the indicator that my random walk exits at 0 at the nth step, and that tau is equal to n. Okay. So now I take this expression and substitute it back into the expression for the log determinant. And I get the following formula just by resumming. So this is just the density of my random walk at the exit time, and the density is computed at 0, weighted by lambda to the power the exit time. Okay, so now I reformulated the problem of computing the log determinant in probabilistic terms. Now use some standard tools, something like the Ballot theorem. In other words, you use the cyclic symmetry of the random walk, and Speer-Anderson formula, which actually gives you the joint law of the exit time for a single barrier and the exit position in order to compute this determinant. And you will start in the limit of large times, you will start getting formulas which I announced on the previous slides. And then you take these formulas and analyze all the examples which I mentioned at the beginning. And this is the end of my talk.
Okay, thank you very much for so interesting explanation with a lot of different routes. And now maybe somebody have questions or comments, please. Okay, I have some questions. By the way, this CATS formula, we mentioned it last seminar when Nikolai Ivanovich Partenko gives a talk about Brownian motion with membrane, and he needs calculations with the time, with the local moments of the local time, which is exactly the same. Okay, so you asked about examples without this special structure of Pfaffians. When you considered the well-known models and just said that such a structure we have due to duality. Then let me ask you firstly, if we change the law of one particle in this coalescence processes, maybe we will have the same structure. We suppose we take just Brownian motion with shift. Then we have duality just minus the shift, and more or less we have the same. So I think that we will have the same structure. So it seems that it heavily depends on the dynamics of the particles. We have to find something, some dynamics where there are no duality. Yeah.
That's right. Yes. Yeah. Exactly. Yes. You're absolutely right. So if you have, imagine that you replace your Brownian motions with independent Ito diffusions, you will get the same answer. You will
yes, exactly. Yeah, it seems yes.
That's absolutely right. So the dual, and I think you are right. If I were to go and look for counterexamples, I would look for models which do not have the simple dualities. Yes.
It can mean that we have maybe some non-Markovian processes for motion of one particles.
Right.
Maybe. Yes. And from this point of view, let me call you the process from my book where we have equation with interaction. So we just consider the equation, stochastic differential equation, where the coefficients depend on the mass distribution of all system of the particles. Then one particle has no Markovian trajectory now, only together with all mass distribution of all particles.
Right.
In this case, I think that we have no simple dual process, because I spent a lot of time when I invented this equation with interaction. I spent a lot of time trying to find dual processes, but I was not succeed. So maybe due to this circumstance, we can have still some simple structure, because it is very close to structure of system with independent motion, but not the same. So at least one can try. At least one can try.
Thank you very much. Yes.
By the way, the same happened maybe if we just take a random change of the time in Aratia flow, for example. Suppose that this changing of the time depend on the space and is random.
Right. Yes.
Then maybe we lost good duality. But still, maybe one can still keep some structure of point process. Right.
Yeah. I can certainly say that if you have a deterministic time change, then all the dualities survive.
Yeah.
And the Pfaffian structure also survives. And if you have a random time change, I need to check. I mean, one worry is that the answer will not necessarily, so the answer will certainly be an expectation of Pfaffian point process.
Exactly, like some mixture.
That's right. And then you need to check whether it's a Pfaffian point process or not. Yeah. Thank you very much. And it's a wonderful book, by the way. Thank you very much for sending me a copy.
Thank you again. And maybe some other questions or comments. Let me another one. We have with Nikolai Vovchansky, who is our colleague, and he is present here. We have an article related to another representation for point densities for Aratia flow with shift using Gersonov theorem for stochastic flows, where we can just like perturb this Pfaffian structure with the expectation of some stochastic exponents. And again, I think maybe this is just another way of thinking about this structure of point process, because the initial question about the emptiness of the interval 0L remains valid even if we break the Pfaffian structure. Yeah.
Right. Right. Yes. Yeah. That is a very interesting question. That is a very interesting question, because as you say, Pfaffian structure is fairly delicate.
Yeah. Yeah. It is. Okay.
Okay. Thank you very much.
Thank you very much again. And now we finish our session for today. Georgi, maybe you know who will be the next speaker?
Next speaker will be Vitaly Konarovsky.
Okay. By the way, Oleg, it will be, I think, at least I don't know the title, but I must say that Vitaly is working with a very interesting modification of Aratia flow, where the mass of the particles don't remains to be one. But if we have two particles coalescing, then mass became to be 2, but diffusion became to be 1/2.
Right.
Like this one, yeah. So it is slightly different things, and but still it has a lot of open questions. So if you will have a time, please visit our seminar next week.
Yes, I'm very lucky. This term I don't have to teach during the slot.
So, very good, very good. Yeah.
Andrei Anatolyevich, by the way, we have already discussed with Professor Zaboronsky that model a few years ago when I was
yes, when Vitaly visited Warwick. And Vitaly, if you start calling me Professor Zaboronsky, I will call you Professor Konarovsky.
Okay, I'm sorry.
Maybe this is intent of Vitaly, yeah?
Okay, noted.
Okay, so
my next talk will be about a different model. It should not be about the type of coalescing particle system.
Okay,
unfortunately.
Right.
But please come if you have time.
I will definitely come. Thank you.
Okay, thank you very much again. And now we stop our session. Bye, everybody.
Thank you very much. Goodbye, everybody.
Thank you and bye.